I was in charge of the microcontroller and the programming. When I first started this, I took into many considerations, including how many input-output pins would we need, what size of bus would we need to control all of our data, what clock source would we use, and what language would we use to implement all of these functions. When I first looked at the input-output requirements at the beginning of last semester, I thought we would only need about 12 input-outputs, and I was very incorrect on that. As we went along, I realized we needed a lot more. First of all, most of these were correct. The main thing that jumped it up was the 7 inputs for the keypad. But we had the sensor for the pills in the cup, one sensor for the pill dropping into the cup, one switch for the cup placement or cup removal, a light that would turn on to allow everyone to see that the pill was dispensing, say they were out of the room or away from their buzzer, and they noticed the light was on. It would also allow them to take the pills if the environment was dark. One for the LCD output, once again the 7 for the keypad input, 8 for motor control, which consisted of, as Jacob mentioned earlier, 4 to send the signals to the motors, and another 4 for the switches that would be controlling the stopping and starting. Real quick on the way these switches worked, they would remain open in those slots that he demonstrated, and it would close, and the power would remain on as the switch was closed, and then when it opened again, it was perfectly lined up where the pill would drop. So it was an open, close, open routine that we used to control the motor. And finally, one for the RF signal. When analyzing the data bus size, we decided that a maximum of 8 bits was all we needed to control everything. It was sufficient for the LCD output and covered the data transfer for all other components. The clock source we ended up using was a 4 MHz crystal oscillator, and when programming it, we selected the XT configuration bit in the microcontroller, which just means an external timer. There were 2 other options, but XT seemed to work the best. Programming language, we went with C language. Micro C evaluation version was the compiler I chose to use. It was free and it had 2 months of free usage as if it were the pro version. And that originally we wanted to use one with a software called Micro Lab, or MP Lab. And that just didn't work out, and Micro C seemed to be a lot better. On our first proposal, we were going with a pin that was actually 18 pins, and that was when I thought we'd only need 12 input outputs, but we had to upgrade to the PIC 16F877A. This one supports the C language, has the 8-bit data bus we needed, and 33 programmable input output pins, which is more than enough to cover everything that we have to do. For the programmer, I went with a simple JDM programmer, which works by when you compile the code, it outputs a hex file that represents all of the instructions, and you use a software called WinPic 8000 that would load this onto the microcontroller. WinPic was a completely free program that's open source, available online. Cost breakdown, the PIC was about $488, programmer kit was $20, our various components that I used roughly averaged around $20, the micro C compiler was free, and with shipping and handling, everything was about $50. Of course, I went through numerous PICs trying to understand how to use them, so the cost for me was a little bit more, but the cost of what is in there is about $50. As for programming, I approached it by first looking at the user interface. I decided it had to be intuitive, as in easy for anyone to use, robust enough to handle various error inputs from the user, or if there was an error in dispensing, and configurable so that they could change data or update it as they went along. Also, component control was integrated with sensors, in other words, the motors, RF, LCD output, and also input response loops waiting for, say, the cup being removed or a pill being detected. To do the accurate clock, I discovered that the oscillator speed is, or the clock cycle is actually a quarter of the oscillator speed, and we use a timer 0 interrupt, which works by overflowing the 8-bit register that fills every clock cycle. So a quarter of our 4 megahertz is 1 megahertz, divided by 256 is 3,906.25. I multiplied that by 4 to get a whole number, which is 15,625, and so we use that to increment the seconds by 4. Input from the user consisted of selecting the number of pills and the intervals to dispense, and also the clock information, which includes the current day. Pill dispensing algorithm would be check for the number of pills to dispense, check if the current day is matching the day that should be dispensed. If we have a match, we check for a matching time in the number of minutes and number of times to dispense in that day. If there's a match there, we dispense the number of pills for the specific dose. check the rest of the trays, and then signal the user to take their pills. Following that was a menu button that allows them to operate various debugging functions such as dispensing the contents of the trays, entering pill data, clock information, and viewing logs. I'd like to pass it on to Omar Shabaik for the RF.